Hello and welcome back to Unit 6A. We are on Section 3, Angles Related to a Circle. This one is kind of a long section, so I'm just going to encourage you to do this section over 2 days maybe, and I'll give you sort of a good place where you can stop and take a break. So the beginning of this unit, I'm going to introduce to you all the different types of angles related to a circle. Then the second part of the video will be finding missing values using those rules that we just learned. So let's start the first half of the video just kind of thinking about the different types of angles and arcs and relationships that we're going to have. So we're going to start with the very first row is just kind of separate from the others. There's really one example of this. This is angles with vertices on the, and we're going to call this the center of the circle. And so we call this a central angle. A central angle is an angle whose vertex is on the or at the center of a circle. So, kind of looks like this, like that. We've got, let's call this angle AOB. And so the rule for angle AOB, so if I said, the measure of angle AOB, it's actually equal to its intercepted arc, which is arc AB. And oops, I gotta fix that, sorry. The measure of angle AOB is equal to its arc, the measure of the arc, AB. So basically, like that's the arc right there. The measure of the angle O is going to be equal to the measure of its intercepted arc. Okay, so that's central angle. When you have a central angle, the rule is the angle and the arc are equal. Okay, there's going to be like 4 things that could happen. This is the situation in which we have equal. Okay. Now, in our second part, we're going to have angles with vertices that are on a circle. So angles with vertices that are on a circle are called either an inscribed angle or a tangent chord angle. An inscribed angle we'll work on first. An inscribed angle is an angle whose vertex is on the circle, which means it looks kind of like this. It sort of like stretches back, vertex on the circle. Almost looks like it's made with 2 chords, something like that. So let's call this CXD. So it's not a central angle like we see above it. Angle X isn't going to equal its arc. Okay, we do have this arc, right? We have this arc CD here. Okay, but angle X isn't equal to it. Angle X is actually equal to half of it. Okay, so the measure of angle CXD is actually equal to half the measure of arc CD. It's actually equal to half the measure. Okay. And another type angle that has its vertex on the circle is what we call a tangent chord angle. And it's an angle formed by a tangent segment and a chord of a circle. So if let's say we have a chord, maybe like this here, and then we have this like tangent segment. Goes right through it like that. So let's say that's the vertex. And we'll just call this angle EF, and then I'm going to put the G right here. So we do, in fact, have an intercepted arc. It's right there. Okay. That rule is going to be the same. It's because the vertex is on the circle, the angle is going to equal half of its intercepted arc. So the measure of angle EFG is still equal to half the measure of its arc, which is actually EF. Okay. EF is the arc that it intercepts. So when angles have their vertices on a circle, like we see with X here, the inscribed angle, and angle F here, the tangent chord angle, the rule is going to be that the angle is equal to half the arc. Okay, so we've got central angles equal their arcs. Okay, inscribed and tangent chord angles, they're going to be equal to half of their arcs. Okay, a third scenario would be angles with vertices that are inside but not at the center. Okay, these have a special name. They're called chord angles. So let's say we form like 2 chords. So there's a chord, there's a chord. So we have an angle right here. There's actually 4 angles at that point. But let's say we're talking about angle, we'll call this A. I'm going to call that vertex E. And let's call this B, and then we'll call this C and D. So we have, let's say, angle E. So the angle E could either be this one, or it could be the one on this side, because you remember vertical angles always equal each other. So to find the measure of that angle, what we're going to need to use is going to be 2 arcs. We're going to need this one and this one. So we call this a chord angle because it's an angle formed by 2 chords of a circle. And the way we're going to find the measure of angle E, in this case it's angle, we'll call it AEB, okay, it's going to be equal to half, and we're going to have to add the 2 arcs together, so it's like half the sum of the arcs. So we're going to take arc AB plus arc CD. So we say the measure of the angle is equal to half the sum of the intercepted arcs. Say half the sum of the intercepted arcs. So that's really our third scenario. And then there's one more scenario that has 3 pictures with it. And this is going to happen whenever angles have vertices that are outside of a circle. And I will show you some examples. There are 3 ways that this could happen. First is a secant-secant angle, and it's an angle formed by 2 secants. Okay. So an example of that could be, let's say here we have a secant and then another secant, something like that. So let's just call this W, we'll call this X, Y, Z, and let's just call this A. So you can see that we've intersected the circle in these points that actually cut off 2 chords. They cut off 2 arcs of the circle. So if you notice, you have like a little arc and you have like a bigger arc. Okay? So what we're going to do is, to find the measure of angle A, we're going to actually take half the difference of those arcs. So always take big arc minus small arc. So to find the measure of angle A, we're going to take 1/2, and then you're going to take the bigger arc, WX, minus the smaller arc, YZ. So we call that half the difference of the 2 arcs. And it's the same rule for the other 2 pictures. The pictures are just going to look a little different because for a secant-tangent angle, will be formed by a secant segment and a tangent segment. Okay, so, very similar. We're going to have this, we'll have this secant, so right through. But then on this side, it's actually a tangent, maybe something like that. So your arcs that you have are, you have this bigger one, of course, but then you actually have this littler one that kind of butts up right to it. So the 2 arcs are right there. They sort of run right into each other. So we're going to sort of think of them as being separate. So again, I'm going to make this A, and then we'll call this L and N, and we'll call this M. And so the measure of angle A, it's the same rule. We still want to take half the difference of the arc. So you're going to take the bigger arc, which is the far away one, LM, and you're going to subtract the smaller arc, NM. So again, half the difference of the 2 arcs. Okay, one more picture. This one would be the tangent-tangent. So we've seen tangent-tangent rule before for segments. Now we're going to get a tangent-tangent rule for the angles. So an angle formed by 2 tangent segments drawn from an exterior point. So let's say we have something like this. So there's a tangent, and then here's a tangent. So what it does is it breaks the circle into 2 arcs. You've got this close-up arc here, and you have this far-away arc here, but they actually butt right into each other. We use the whole circle in this situation. So we'll call this angle A again, but this time we'll call this H, and I'm going to call this J, and I'm actually going to put a letter here so we can refer to it, since that's a really big arc. So again, the measure of angle A is equal to half the big arc, HIJ, and then take away the small arc, HJ. So we say half the difference for this rule. So we get half the difference when the angle is outside the circle. So it seems like a lot of pictures, but it's really only 4 places that the vertex could be that we have to know. There's really just, the key is really just the location of the vertex, and that's what we're gonna do in this chart. We're gonna try to make this, summarize this for you. So the key is the location of the vertex. Okay, so when the vertex is at the center, the angle equals the arc. That's our central angle. When the vertex is inside the circle, but not at the center, that was our chord situation, we're going to use the angle equals half the sum of the arcs. When the vertex is on the circle, that was the inscribed angle or the tangent chord angle. The angle just equals half the arc. And finally, when the vertex was outside the circle, the angle is half the difference of the arcs. So if you wanted to take a break now after getting all this information down, the next half of the lesson is going to be on solving for missing angles and arcs of our circle problems. Okay, so if you need to take a break now, you may do so, but I'm going to keep going, and then you can come back to the video when you're ready. All right, so we're going to go ahead and start finding some measures. Now, the typing programs don't give you an arc option, so whenever you don't see the arc, it just says like measure AC, you have to know that they mean arc AC, so that's what they're looking for. So if the measure of arc AC is 112, we want to find the measure of angle B. Okay, so we want to remember the rule for if the vertex is on the circle, remember the angle is half of the arc. So to find angle B, we're going to take half of 112, or 112 divided by 2. So measure of angle B is 56 degrees. Okay. In number 17, they want us to find the measure of angle N. So again, the location of the vertex at the center. That means it's a central angle, and central angles equal their arcs. So 2x equals 5x minus 39. If I subtract 5x, then I get negative 3x equals negative 39. Divide, and x equals 13. To find the measure of angle N, I'm going to take 2 times 13 to get 26 degrees. So that was inscribed angle, central angle. And we'll keep going. On the next page, it says find the value of x. Okay, so now I see that the angle is inside. The vertex is inside the circle, but it's not at the center. So for that rule, remember that means that the angle, 72 degrees, is equal to half the sum of the arcs. So half of x plus 21. So to solve that, I'm going to multiply 72 by 2 to make it 144 equals x plus 21. And then subtract 21, and I get 123 for x. Now number 19 is a little bit of a variation of that problem. We have, they're looking for y, and y is actually not, it doesn't have any arcs associated with it. Like if you look at y, we don't really know these two. So I don't think we're going to start there. Let's start maybe and just adjust the problem a little bit. And let's say we want to find x. And then we can use it to help us get y. So inside the circle, but not at the center, the angle equals half the sum of the arcs. So half of 29 plus 47. So when I add those together, I get 76. And half of 76 is 38. So x equals 38. And x is next door neighbor to y. They form a linear pair. They're supplementary. So if I want to find y, I just have to take 180 minus 38. And y is 142. So we kind of had to work around this one to get to our y. Let's fix this a little bit. That's actually degrees, not, almost looks like a square there. So let's change that. that was actually x equals 123 degrees. Okay, number 20. So here I see a vertex that's sitting on the circle. Measure of arc DE is 80. So I'm going to put that here. There's 80. And then it says find the measure of angle DEF. So I want to find this angle right here. So on the circle means it equals half of its arc. So measure of angle DEF is going to equal 1/2 of 80, or 80 divided by 2. So measure of angle DEF equals 40. So some of them go pretty quick like that. Now number 21 says that FK is tangent at K and find the measure of angle F. Now F is outside the circle. So outside the circle means I need big arc, take away small arc. I know small arc, but I have to get the big arc. So remember, a circle adds to 360. So if I have 160 already, that leaves 200 for the rest of the circle. So that's actually 200 degrees there. So now to find the measure of angle F, I have to do half the difference. I need big arc, 200, minus small arc, 60. So half of 140, measure of angle F equals 70. We should see a very similar situation in number 22. A is outside the circle. So that means I'm going to need big arc, take away small arc. Okay. So I'm going to need the measure of angle A is equal to half of 100 minus 20. So we do half the difference of the arcs. So that's half of 80. Measure of angle A equals 40. I see an angle outside the circle again in number 23. Okay, but we have less information here. Let's see, we have that little arc. We don't have this one, but we have the really little one. We have this 20 right here. Okay, so we got to figure some things out. I notice that this is a diameter, which means semicircle is 180. So if I take 180 minus 20 minus 104, I'm left with 56. So sometimes you have to work out the arc that you need first before we go to the rule. So now, since A is outside the circle, we need half the difference of the arcs. So we're going to take 56 minus 20, which is 36, which means measure of angle A equals 18 degrees. So we have some good examples there of the different places the vertex could be. So now for 24, I think I want to give you a little time to try that one. So maybe pause the video and see if you can use central angles only to find measures of each intercepted arc. So if you want to pause the video, go ahead, do that, and then come back. Okay, so what I like to do on these problems is match up central angles with their arcs. And so, for example, like I know that JK would have to be 75 since its angle is 75. Let's make that a little nicer. Okay. And then since this is a straight line right here, I know the next door neighbor angle to 75 has to be 180 minus 75. And 180 minus 75 is 105. So that means this arc has to be 105. So a semicircle has to add to 180, a straight line has to add to 180. So that's 105 right there. Okay, then there's a couple ways you can work with, like these are vertical angles. So if that's 75, this is 75. So we know that has to be there, which makes this arc 75. Okay, or you could use the supplementary angles again. And then we know that this is 90. So of course 90 would be JN. And then you can use a couple things, like we know JM would have to be 105 since that's a vertical angle, or you can think of these two arcs added to one, subtracted from 180 will give you that. So 90 plus 75 taken away from 180 would leave just 15 left for that arc. So once you fill in all that, getting the information for your arcs will go really fast. So I'm just going to put all these little arcs in here so we remember that that's what we're looking for. So JK we know is 75. KL we found is 105. LM 75, JN 90. So we did all these, you know, without even looking at the problem. It's just nice to have them filled out in advance. We get 15 for our MN. Okay, now we have JKL, so I just kind of want to follow that one. So J to K to L, well, that's a semicircle, so we know that's 180. JMK. Now, when you do JMK, you want to go from J to K, but you need to go through M. So that's actually a really big arc. Okay, it's from J through M all the way to K. So that's actually everybody but the 75. So the easiest way to do that would be to do 360, take away 75. And if you do that, you have 285. Oops. Okay. And so that's just kind of a nice way to get that, is to use, you know, use that whole circle, that 360, and that'll get you what's left. Now, JLM, we can kind of do the same thing. This time I have to go from J to M, but I have to go through L. So I have to go this way. So now it's J to M. So you could either add 75, 105, and 75. That's one way to do it. Or you could do 360, take away the part that we don't want, which is 105. Either way, you get 255. And then the last one is LNJ. L to N to J, we're looking at another semicircle, so that's 180. So that was strictly central angles. So time for you to try one on your own. So I'm going to ask you to look at number 25. You can pause the video for that one. Okay. So this one's asking us for the measure of angle CAT. I'm sorry, the measure of arc, CAT. So that's C through A all the way to T, which is all of that. Okay. And that is 320, they tell us. So that 320 degrees. So that's most of the circle, right? That only leaves you with 40. So if we put 40 for CT, well, S is a central angle. So X has to be also 40. So it's nice to use that 360. All right. These two problems, 26A and B, involve inscribed angles. Okay, so if we remember, an inscribed angle is equal to half of its arc. Okay, well, usually we know the arc, and we divide by 2 to get the angle. But if we know the angle, we're going to have to multiply by 2 to get the arc. So 82 is equal to half of X. So 82 is half of who? Well, if we double 82, we'll get X. So that's going to be 164. So if X is 164, that makes sense because 82 is half of it. Same with over here, 100. The angle is equal to half of the arc. So 100 is equal to half of 4x minus 16. So if I double 100, I'll get 200 equals 4x minus 16. If I add 16, then I get 216 equals 4x. Divide by 4, and I should get, I think, 54. 54 equals x. Which should make sense because if I were to do 54 times 4, I get 216 minus 16 is 200. And 200, okay, is twice 100. 100 is half of 200. Okay, so there's a couple inscribed angle problems. 27 wants us to draw our own picture. Find the measure of an inscribed angle if it intercepts an 84-degree arc. All right, so let's make a picture. And draw a circle. Okay, then let's make an inscribed angle. So there's my inscribed angle. Remember, it's formed by 2 chords. Its vertex is on the circle. And it intercepts an 84-degree arc. Okay, so remember your angle, call that x, is equal to half of your arc. So half of 84 is 42, and that's all you have to do. I think we finally made it to the last page of this section. And there's going to be some you try at the top. We'll start with that one. So if you want to take a minute and pause the video. Think about what type of think about what type of angle it is, and see if you can solve. So hopefully you gave yourself a chance to try. So I see an inscribed angle, which means the angle 2x plus 6 is equal to half of its arc, which is 200. So 2x plus 6 we can say is equal to 100. Subtract 6. 2x equals 94. Divide by 2. And x is 47. All right, we have one last little theorem that kind of rounds up everything. It just sort of adds, actually we have two last little theorems. They kind of add a couple of neat little shortcuts to our problems. The first is a picture we've seen before, the tangent. So we already know on this picture how to take, big arc minus small arc. We already know how to do that. But there's actually another way that we can get some relationships here. So a tangent angle, angle C, is actually supplementary to its intercepted minor arc. Okay, which is actually BD, arc BD. So what that means is the measure of angle C added to the measure of arc BD is always going to equal 180 degrees. And again, that has everything to do with the fact that we have an entire 360 that we're using for the circle. So I'll show you how this works. If angle F is a tangent angle, and angle F is 6x, so we'll put a little 6x in here, and arc OE is 15x plus 33, so that's this part right here, 15x plus 33. We don't really know anything, about this arc. So we can't just go like big arc, take away small arc. We can still look at the arcs, but we just don't have the same information. Like here's the really big arc, here's the small arc. But we do know that when you have two tangents, the arc and its angle, they're going to add to 180 degrees. So you could actually take 6x plus 15x plus 33 equals 180. So then that's 21x plus 33 equals 180. Subtract 33. 21x equals 147. Divide by 21. X equals 7. Okay, so now let's go back and find out what they actually asked us to find. So they want us to find arc ODE. So we probably should first find arc OE. So if we do 15, let's do OE. If we do 15 times 7 plus 33, we're going to get 138. Okay. Then the big arc, we'd have to take 360 minus 138, and that's going to be 222. So now we know this is 222. Okay, so just remember, those two add to 180. There's a lot of little rules. Our very last one is a theorem about angles inscribed in a semicircle. So if you notice, this here is a diameter, which means that this is 180 degrees. Now, if you also notice, this angle here is inscribed, which means it equals half of that 180. So guess what? It's a right angle. So if an angle is inscribed in a semicircle, then it is a right angle. So I'm going to give you some time now to work on problem 30. See if you can figure out all of those angles or arcs. Remember, some of these are arcs, so if you don't see the symbol, you can draw it in yourself and we can find each one of these. So you can pause the video and try problem 30. Okay, and then I'll walk through each one. So they gave us some given. So it says angle DEC is 50, so that's 50 right there. ABD is 30, so that's like this little one right here. That's 30. That's all we need to find all this information. Let's start with CD. So CD, central angle, has to be equal. That's also 50. BC is the rest of the semicircle. Okay, so 180 minus 50, which which is 130. CBD, look at that one. CBD is intercepting this 50, but it's on the circle, so it's going to be half. So half of 50, that's 25. Let's see, A, B, C. Okay, ABC is going to be half of whatever AC is. I don't really know AC yet. Let me see what I can do. So if this angle here is 30 and it's inscribed, then I can double it to get AD. So that means that's 60. So really, if I want to get ABC, I can add these two together and take half of it. So 60 plus 50 is 110. It's really just half of 110, which is 55. Angle BAD. BAD, it's inscribing a semicircle. That means it's a right angle. That's 90. Oh, except for they're not asking for angle BAD. They're asking for arc BAD. So sorry. Let's get rid of that. I need arc BAD. Arc BAD is 180. That is a semicircle. I think they get to the other one, letter G. All right, arc AB. Arc AB is this one here. Well, if this is 60, the rest of the semicircle would be 120. And now angle BAD. Back to that one. So angle BAD is half of 180, which is a right angle 90. All right, that was a long video. Hopefully you spent some time thinking about the problems, and we have a lot more practice we're going to do in class. Thanks for hanging on. Have a great